Okay, so today we cover logarithms. So last class, we learned about exponential functions, and we learned that exponential functions were one-to-one. Well, if you are a one-to-one function, this means you have an inverse, and the inverse of the exponential function happens to be the logarithmic function. Okay. So the definition of a logarithmic function, the logarithm to the base a, where the base has to be greater than 0 and not equal to 1, is denoted by y equals log base a of x. If and only if x equals a to the y. So what we're saying with this statement is that the log function is true if and only if we can convert it to an exponential function, such as x equals a to the y. This relationship shows that they are inverses of each other. Okay. The domain of a log function is going to be all values of x greater than 0. A logarithm is a name for a certain exponent. So log base a of x represents the exponent to which a must be raised to obtain x. So logarithms, they're actually very useful. They're able to put extremely large or transcendental numbers into a smaller output for us humans to understand. So when an earthquake hits a city, all we say is, hey, that was a 7 on the Richter scale. And people are like, ooh, 7, that's crazy. But in reality, you're shaking a whole city. You're shaking possibly a whole state. So the number is actually way, way larger than that. So logs take extremely large values and put them in a simpler format so it's easier to work with. Okay. Just like exponential functions go on infinitely. So the values get larger and larger and larger, and the inverse logs can put those values into a smaller perspective. Okay. So now for the next example, we are going to convert our logs into exponential functions. Okay. So we'll start with a. Y equals log base 3 of x. So the base of the log will become the base of the exponential function. So what we do here is we say the base of 3 is going to be raised to the power of y. So what we have here so far is 3 to the y, and then we set it equal to the inside of the log, which is x. So take the base of 3, raise it to the outside number of y, and set it equal to the inside of the log, which is x. That is it. That is how you convert from log to exponential. Okay, let's try it again. B, 4 equals log base 3 of 81. We do the same thing here. You take this base of 3, raise it to the outside number of 4. So you get 3 to the 4th. And then you set it equal to the inside of the log, which is 81. And there you go. And this is actually a true statement. 3 to the 4th is 81. Okay. And again and again and again. So next, y equals log base 5 of x. Take the base of 5, raise it to the outside number of y, and you get 5 to the y equal to the inside number of x. That's it. And then D, same thing. -1 equals log base 5 of 1/5. Take this base of 5, raise it to the outside number of -1. You get 5 to the -1, set it equal to the inside of the log, 1/5, which happens to be another true statement. 5 to the negative 1 is 1/5. Okay, and that is how you convert from log to exponential. So that's going to be very useful when we actually have to find the inverse to graph these. Okay. Now the next example is going to be changing exponential equations into logarithmic functions. Okay. So one thing to remember is that now the base of the exponential function will become the base of the logarithm. So we'll start with A. So the base is 1.2. So what we're going to say is log base 1.2 of the outside number of m set equal to the exponent of 3. There you go. So the base of the exponential becomes the base of the log. That outside number goes inside the argument of the log, and then you set it equal to the exponent. So that's how you go from exponential to logarithm. Okay. Again. Here's our exponential base, e. So we're going to say log base e of the outside number of 9 equal to the exponent of b. Done. And you can always check your work by converting back from log to exponential. So if we took this example, it would be e to the b equal to 9. And we have the same problem that we started with. Okay. All right. Again, base is a. So we get log base a of the outside number of 24 set equal to 4. There it is. And that is going from log to exponentials and then exponential to logarithms. And we are able to do this because they are inverses of each other. Okay. Any questions on that? All right. Let's keep going. Example 3. We are now going to evaluate logarithmic expressions. So here we're going to be given a logarithmic expression, and the only way to evaluate it is to change it into an exponential notation. So here, once again, the property, if y equals log base a of x, then we can convert it to exponential as a to the y equals x. So for number 1, we have log base 2 of 16. So what we're going to do is let's go ahead and set this equal to x. We can even say y, whatever variable you choose. We'll just set it equal to x. Now, in order to simplify this log expression, we are going to convert from log to exponential. So we're going to say log base 2 raised to the x. So you're going to get 2 to the x equal to the inside of the log, which is 16. So now we have this exponential equation, 2 to the x equals 16. which we can now use methods that we learned last class and change 16 into a base of 2. So this will become 2 to the x equal to 2 to the 4th. And since the bases are the same, you set the exponents equal to each other. And here, x just equals 4. So what we're saying is that log base 2 of 16, the answer is 4. So log base 2 of 16 is 4. Okay. Do it again. All right. So let's go ahead and set this equal to x again. And we'll convert from log to exponential. Base 5 raised to the x. So you'll get 5 to the x equal to 1. 5 to the x equal to 1. Now, how do we solve for x? Well, if 5 to the x equals 1, remember that anything raised to the 0 power? Good. Anything raised to the 0 power is 1. So this means that we can actually rewrite this as 5 to the x equals 5 to the 0th. And now, same base, therefore, x is 0. There you go. All right. Again. So we'll set this equal to x, and I'll say log base 1/4 raised to the x. So 1/4 raised to the x equal to the inside 1024. Okay, so 1/4 to the x raised to the 1024th. Well, I'm going to assume that these have the same base of 4. So 1/4 to the x, I can rewrite as 4 to the negative x. Again, to do that, 1/4 to the x becomes 4 to the negative 1 to the x, which then becomes 4 to the negative x. So we just rewrite that exponentially. Okay. And now 1024. I'm going to say that is what? 4 to the, nope, not 4 to the 4th. 4 to the 5th. Good. 4 to the 5th. So now same base. Negative x equals 5. And therefore x equals negative 5. Okay. 4. Let's keep going. Let's go ahead and set this equal to x again. Take this base of 6, raise it to the x. 6 to the x equal to the inside of the log, which is the square root of 6. Okay. Well, now we see we have the same base, but what is another way to rewrite the square root of 6?
6 to the 1/2.
Good. 6 to the 1/2. Same base. X now equals 1/2. Okay. All right. Log base 3 of 1/27 equals x. rewrite 3 to the x equals 1/27. Okay, so lucky for us, 27 can be turned into a base of 3. So this will become 3x to the 1/3 cubed. Almost there. What is another way to rewrite 1/3 cubed?
3 to the negative 3.
Good. 3 to the negative 3. Same base, x equals -3. And there you go. That's how you solve these logarithmic expressions. Convert them to exponential, and then use the exponential equality that we learned last class. Any questions on those ones? Logs are definitely crazy, but they do make math a lot simpler, especially when you get to calculus. There's going to be something called logarithmic differentiation, and you can either spend 30 minutes to an hour not using logs, or you can spend at least maybe 2 minutes to solve the problem. That's the difference. Logs will make your work easier. Okay. All right, so once again, we're going to cover the domain of a logarithmic function. So the log function has been defined as the inverse of the exponential. So I've been saying that. So if f of x equals a to the x, then the inverse is going to be log base a of x. The domain of the log is going to be the range of the exponential function. So remember, with inverses, your domain and range switch places. So this means that the domain of the log will now be 0 to infinity. The range of the log will be the domain of the exponential function, which is all real numbers. So to state it again, here are the properties of your common log function. The domain is 0 to infinity, and the range is -infinity to infinity. Okay, so this means you can't type or you can't find the log of a negative number. So if I said the log of -1, this would not work because the domain is 0 to infinity. It's all positive numbers. Okay, let's go ahead and practice finding the domain of a logarithmic function. So for number 4, you have f of x equals log base 2 of x plus 3. So to find the domain of a logarithmic function, we take whatever's inside the log and set it greater than 0. And now all we have to do is solve for x. So here we get that x is greater than -3. So the domain for this log will be all values greater than -3. Or -3 to infinity. Okay. So that's finding the domain of a log. Whatever is inside, set it greater than 0 and solve for x. Let's do it again. Second one, g of x equals log base 5 of 1 plus x over 1 minus x. Okay. So for this domain, you're going to take 1 plus x over 1 minus x and set it greater than 0. Well, what we have now is something we've worked with before. This is now going to be a rational inequality, which means in order to solve it, we need to find x values from the numerator and the denominator, and then plot them on a number line to see what's going to work. Okay. So here, I'll just say numerator, which is 1 plus x, set it equal to 0, and x will equal -1. There's our first value. And then denominator, set 1 minus x equal to 0. And you'll get 1 equals x. Okay, but since this isn't denominator, we know this can't happen. So we put 1 cannot equal x, or x cannot equal 1, or the denominator becomes 0. Now, put this on a number line. And there's negative infinity, there's infinity. And here's going to be -1, and here's +1. Now we're going to pick test numbers on these intervals. So from negative infinity to -1, let's go ahead and pick -2. From -1 to 1, we'll pick 0. And 1 to infinity, we'll pick 2. Now take all of these numbers and plug them into that inequality above. 1 plus x, 1 minus x. Oops. So we'll say at x equals -2, you get 1 plus -2 over 1 minus -2. And here you get -1 over 3. So this means that from negative infinity to -1, we are negative, which means we are not greater than 0. So there's our negative. Okay. And then for x equals 0, we get 1 plus 0 over 1 minus 0, which gives us 1. So 1 is definitely greater than 0. So this checks out. So this means you'll be positive. This is less than 0. So that does not check out. Okay. Last number to try is 2. 1 plus 2 over 1 minus 2. And you get 3 over -1, which is not greater than 0, so it doesn't work. So that means you are negative. Okay, so we were only looking for values of x for an interval of x that would be greater than 0. That would be positive. So what is my only interval here?
0, 0. Oh wait, sorry.
-1 to 1.
-1 to 1. Yeah.
-1 to 1.
Excluding 1, though, right?
Exactly. Excluding both of them. Because our inequality just says...
Yeah, because the -1 up on top would be 0.
Well, you can have a 0 up there, but our inequality just says greater
Yeah, but
than.
I thought the log had to be greater than 0.
Yeah. Yes. So you are correct.
Because your number line looks like it was solid compared to the 1. The -1 looks solid compared to the 1.
There you go. Okay. So -1 to 1. Okay. Or if we wanted set notation, we would say -1 less than x less than 1. Okay. Hey, that was fun, right? We've done this before, though. That's a rational inequality. Okay. Next. H equals log base 1/2 of x to the 4th. All right. So here, for our domain, you're going to take x to the 4th, which is inside, and set it greater than 0. Okay. Well, what we're going to do is, of course, take the 4th root. Oops. Take the 4th root of both sides. And remember the rule for square roots or even roots. If I have the square root of x squared, the outcome is the absolute value of x. So that's going to be the same result here. You are going to get the absolute value of x is greater than 0. Okay. So what does the absolute value mean? We can plug in anything negative and it will come out what?
Positive.
Positive, right? So what this absolute value is telling us is that, can we use numbers headed towards negative infinity?
Yes.
Good, because they'll always come out what?
Positive.
Positive. And then we can still use numbers towards positive infinity, but the only number we can't use is what?
0.
0. So what would my domain be for this log?
Not 0.
Everything but 0. So how would I write that?
Negative infinity to 0 union 0 negative infinity.
0
0 to
to
infinity.
positive infinity. Good. All right. Of course, we could get a little crazier with this one. So if you guys didn't know, the absolute value function is actually its own type of piecewise function. So the absolute value of x can be written as all positive x values for any x value greater than 0. Normally it's greater than or equal to, but can we be equal to 0 in this situation?
Negative.
No. And then negative x for all values of x less than 0. So this is telling us how to write this domain. This says we can use anything below 0 and we can use anything above 0, which is represented by our interval notation here. So it's pretty cool, and it's important to know that, yes, the absolute value function is its own piecewise. And once again, normally you would be greater than or equal to, but we can't in this case because of the log. Okay. Cool. And that is how you find the domain of logarithmic functions. Any questions on that?
No question here per se, sir. Just want to let you know I came in 15 minutes late, so 7:15 actually logged in. My bad on that.
Oh, so honest, John. Thank you.
No soup, sir. No soup for you.
No soup for you.
Need some soup, actually.
It's too hot for soup. Unless you're one of those people who eat soup in 100-degree weather.
It's never too hot
Every-
for soup.
Every weekend. I could get that pho every weekend. Or
Oh,
ramen.
I don't consider pho soup. Those are noodles.
It's
Noodles with
literally
broth.
soup.
Okay.
It's literally soup. The only part of the pho that even matters is the broth.
Oh my goodness. It's pho, not soup. Okay. Noodle bowl.
Yeah, it's not pho noodles, though. It's vermicelli noodles. So
Oh, I know. All right. Let's go. Class is canceled.
I'm fasting. Can we stop talking about food? It's Ramadan.
Oh
Same here. I'm
man.
actually fasting myself.
It is Ramadan. I forgot. I gotta call my friend. Every time I saw Ramadan, I tell him I take him to lunch every day.
Oh,
that's
it's
messed
like,
That's wrong.
so you're gonna
But
send him
then-
pictures of food.
No, but then I do take him to lunch after Ramadan. But we don't work at the same place
Nice.
anymore, so we can't do that no more. And he's
Oh,
back in
man.
he's back with his family in Iraq. So but yeah, I get to message him. Thanks for reminding me, Amir.
You're welcome.
I
All
got really confused for a second there because I saw your battery is low warning come up. I'm like, but I'm on a PC.
That's me, guys. Don't worry. I had my laptop unplugged. It's all okay now. All right. Let's keep moving. Hungry people. All right. So what we have next is something called the common logarithm. So if you see a log equation or function that does not show a base, understand that the base is 10. So the common log, the base is 10. And this is only true if you can convert it from log to exponential and get x equals 10 to the y. So of course that makes sense if I were to put that base of 10 in here and then convert it to exponential, you'd get 10 to the y equals x. So we don't have to put the base in 10. If you just write log of x, it is understood that the base is 10. Okay. So to save some time here, I have the log function and its inverse graphed already. But of course, we're going to find the inverse algebraically. So for the log function, some of the most common numbers to choose, now these aren't common, but these are the best numbers to choose when graphing a log function, are going to be 1/10, 1, and 10. And the reason we choose these numbers is because look at the outputs. The log of 1 over 10 gives me -1. The log of 1 is 0, and the log of 10 is 1. And this is graphed by the red line here. So you see you have the point 1, 10, and -1, 1, 0. And if this graph was big enough, you'd have the point 10, 1. So here is what our log function looks like. And you notice that we will never, ever touch the y-axis. That's because the domain has to be greater than what? Greater than 0. Good. So for this one, it's in red. Our domain is 0 to infinity. The range is all real numbers. And since we never touch 0, this means that we will have a vertical asymptote at x equals 0. Okay. And now we look at the inverse, which happens to be the exponential function. Okay. So remember with inverses that if you have an XY chart already made, then all you have to do is flip those values. So for the exponential function 10 to the x, we get the points -1 and 110, 0, 1, and 110. We have just flipped them over. And that function is represented by the blue graph. Here is the inverse of the common log function 10 to the x, and there's your points. -1, 1 over 10, 0, 1, and then 110 if this graph would fit it. And then again, you realize that you never ever touch the x-axis. We learned this last class. You'll get really close to 0, but you will never touch it. Okay. So this means that for our domain, we are all real numbers, but our range, we go from 0 to infinity. So remember that we take these and we swap them with these. And now our vertical asymptote becomes a horizontal asymptote at y equals 0. Okay, that is the common log function and its inverse. But again, to properly find that inverse, well, we would start off with, I'll say inverse. We would say y equals the log of x. And then remember that you interchange variables. So you would get x equals log of y. And now we're going to solve for y, but the only way to do so is to rearrange it as an exponential function. So I'm going to rewrite the base of 10, and now we will convert. You get base 10, raise it to the x, and you'll get 10 to the x, and then you'll set it equal to the inside of the log. And 10 to the x equals y, which means you finally have the inverse, as f inverse of x is 10 to the x. So algebraically, that is how you find the inverse of the logarithmic function. All right, so there is the common log and its inverse. Any questions on that page? Let's see, where am I? There we go. Okay, well then, let's go ahead and check out the natural log function. So here we have the natural log, which is written as ln of x. And if you ever see the natural log, it is understood that the base is e. And this is true if and only if we can convert the natural log to the exponential function x equals e to the y. So I'll write that down here again. If I had y equals the natural log base e of x, and then rearranged it from log to exponential, we again would do e to the y and set it equal to x. There we go. Now again, you don't need to write the base of e in there. If you type the natural log, it's already understood that the base is e. Okay. And again, these are graphed. So here we have the natural log graphed out. And I have chosen the perfect points for you again. And these only make sense because they give you the nicest outputs. So the natural log of 1 over e will give you -1. The natural log of 1 will give you 0. And the natural log of e will give you 1. Of course, we can prove all of this using a calculator. Okay, and now these points are graphed over here on the right. So the red graph represents the natural log. And once again, we realize that we do not touch the y-axis. So no matter if you're a log or the natural log, your domain is still x greater than 0. Okay, So I'll write that here. Your domain is still 0 to infinity. Your range is all real numbers. And since you do not touch the y-axis, you have a vertical asymptote at x equals 0. Okay. And now if we have the natural log of x, the inverse is e to the x. So once again, take your points and flip them, take your domain and range and flip them. We graphed e to the x last time. So here is a graph of e to the x, and we realize that we do not touch the y-axis. Again, you'll get really, really close to 0, but you will never touch. Okay. So the domain is going to be all real numbers. The range is 0 to infinity. And now, since you never touch the x-axis, you have a horizontal asymptote at y equals 0. Okay. And then, once again, to show you how to get the inverse algebraically, we'll start with y equals the natural log of x. We interchange, and x equals the natural log of y. And then we solve for y. So now I will write that base in just so we can see how to convert from log to exponential. You get e to the x set equal to y. And there it is. You have your inverse as e to the x. Boom. Okay. And now that is the natural log. You can find it as your calculator as the LN button. Okay, so we have common log, natural log. Any questions so far? I think the next ones we are graphing. Okay. All right, number 7. We want to graph f of x equals log of x minus 1 plus 5. Determine the domain, range, and vertical asymptotes of the original function, and then find the inverse, determine domain, range, horizontal asymptote, and of course, graph everything. Okay, so we will start with our log function. So I'll rewrite it down here. A, we have f of x equals the log of x minus 1 plus 5. Okay, so one thing we can find out already is the domain. For this log function, remember, you take whatever's inside the log and set it greater than 0. So you would get x minus 1 greater than 0, and your domain would be x greater than 1, or 1 to infinity. And then, what is the range for all log functions?
All real numbers.
All real numbers. There we go. Okay. Now, this means that we need to find our, our vertical asymptote is given as well. So if you're greater than 1, this means you'll never touch 1. So this means that you will have a vertical asymptote at x equals 1. So your domain and your asymptote, once again, go hand in hand. Okay. for the log function, of course. Now we want to graph this. So this means that we're going to have to use transformations. So let me go ahead and first write the function, the coordinates of the parent function that we found on the last 2 pages. So here's the parent function. For x and the log of x, we had chose 1/10, 1, and 10. This gave me -1, 0, 1. Now, if we transform this, well, look at the function we're given. What type of transformation is that x minus 1? Horizontal or vertical?
Horizontal.
Horizontal. It's a shift to the
right.
So for my transformed XY chart, I'm going to have x plus 1. And then what does this 5 do? What type of shift is that?
Vertical shift.
Vertical.
Good. So that means I'll have y. I'll have y plus 5. Okay. So that means that all I'm going to do here is add 1 to all of these x values. Okay. And then 1/10 plus 1, that gives me 11/10. So you'll get 11/10. But since we're graphing it, we need a decimal number. So this is 1.1. And then 1 plus 1 gives me 2. And 1 plus 10 gives me 11. Okay. And then for your y values, you'll just add 5 to all of these. So -1 plus 5 gives me -4, and then 5, and then 6. Not -4.
It's
sorry.
4. I did the same thing. It's 4.
Just 4. Okay. 4, 5, and 6. So let's go ahead and graph the first function. We're not going to be able to fit, we could probably fit 11 on there, whichever. Okay. So we know we have a vertical asymptote at 1. Okay. So you're going to have, let's see, right here. Here's our vertical asymptote at 1. And then for my graph, at 1.1, we are at 4. So 1.1, and we have 1, 2, 3, 4. We are here. And then at 2, you're at 5, which is right there. And then 11, you're at 6. So 11, we'll just squeeze on there. And we are at 6. So right about there. So with these 3 points, here's what my log function looks like. It's probably a little curvier, but we got it. So here is f of x. Okay. So now it's graphed, which means we can now move on to find the inverse. Oh, I left 5 behind. No. Come on. Nope. Obey me. Oh, about to give up. There we go. Bam. Get it together, get it together. We got it. All right, now we go ahead and find the inverse. Oh, I turned that all, whatever. Okay. So B, the inverse. Let's get started. So we're gonna put this as y equals log of x minus 1 plus 5. And then we're going to interchange and get x equals log of y minus 1 plus 5. Okay. And then go ahead and solve for y. So the first thing we're going to do is move that 5 over. So you'll get x minus 5 equal to the log, and now I'm going to put that base of 10 in there. Log base 10 of y minus 1. And now we are going to convert from log to exponential. So this base of 10 gets raised to the x minus 5. So we'll get 10 to the x minus 5 equal to the inside of the log, which is y minus 1. And now just add that 1 over. And we have the inverse. 10 to the x minus 5 plus 1 equal to y. And we will write it as such. F inverse of x is 10 to the x minus 5 plus 1. And now all our work is made easy for us. We want the domain and range. So the domain and range, remember we take these guys at the top and we flip them. So my range is going to be all real numbers. I mean, my domain is going to be all real numbers, and my range is going to be from 1 to infinity. And if I have a vertical asymptote at x equals 1, this means I now have a horizontal asymptote at y equals 1. And we don't need to pick new points. We are going to take this XY chart and flip it. So I'm going to say X, Y. And now if I do 4, I'll get 1.1. 5, I'll get 2. 6, I'll get 11. And let's go ahead and plot this on the graph. All right. So 4 and 1.1. All right, actually I could draw my asymptote first. There's y equals 1. Okay. And then plot my graph at 4. I'm at 1.1. So 1, 2, 3, 4, 1.1, somewhere around there. And then 5, I'm at 2, right there. And then 6, we're at 11, which I'll just put up here. So here is our graph. 5 on target. And there's F inverse of X. Now remember, if they're inverses, they have to be symmetrical about the line y equals X. Do these functions look symmetric? Maybe not my graph, but what do you guys think?
Yes, it does look symmetrical.
Symmetrical. There we go. Okay, that's everything we have to do for that. Any questions on that? You want the next one, Carl? No?
Yes. Sorry.
Okay.
That took a second.
I was like,
Yes.
no. I was like, oh man. All right. I thought I would have won it either.
That bad, huh? Oh, it's
Okay.
gross.
They're all gross, but whatever. All right. Bingo.
Do. Let me close all my illegal content. I don't have any of that. I'm kidding.
Fish that. Fish that.
There. 6.4. Okay, we just did this one. All right. So let's go to draw. Let's get a small thing, and let's start with blue. Start over here. Okay. There. Start a little bit closer. All right. So we want to find the domain, range, and vertical asymptote of x. Okay. So remember, this is an e to the x function, which looks like this, right? So it's never going to go below x. Or I should say it's the inverse of this. So that's sort of what I think of when I try to think of the domains and range of logarithmic functions. Is I try to think, okay, what is the base of this logarithm? What does the graph of that base look like? So we know that the domain of this has to exist where 3x is greater than 0. So that gives us that x is just greater than 0. So we get domain of f is 3 to infinity. All right. And then I want to look for the range of f, which all of them all have the same one. It's negative infinity to infinity, all real numbers, right? And then my vertical asymptote, well, this has a -1, right? So we're going to take everything on this graph and shift it down by 1. So my vertical asymptote will be at x is equal to negative, not x.
No. I think you confused with horizontal.
Yeah.
Because remember, if it's vertical, the shift wouldn't matter.
Oh, yeah. Yep. You are
So-
right. You are
yeah.
right. So my shift doesn't matter. So my horizontal, just kidding. Vertical asymptote will be at, this is at x equals 0.
There you go.
All right. Cool. So then I'm going to go ahead. Well, I guess I can graph it first. So we'll start with our x and our y. And we'll do negative. Well, let's think about this here. What's good numbers to pick? Because this is ln. Right.
If you want, you can transform the parent function unless you have another way to go about it.
Well, I'm just trying to think here, right? So it's going to be e raised to something, right?
Yeah.
This is going to be the ln of something to get to e, and there's really no like good way to do that. So I'm just trying to think of like what x values do I want to pick to begin with, you know? So I think because the output's going to be wonky because it's ln, you know?
Would it be, I mean, you could do multiples of 3. So like
Yeah.
1/3 and then
Yeah, that's a good idea.
like 1/3 e.
Yeah. Well, you
Yeah.
know, 1/3 times, well, I can't go to 0, right? So we'll do 1/3. And then if you do 0, that won't work, right? So we have to do 1. And then what's another good multiple of 3? Whatever, we'll do 2. The graph's going to be weird. Our output, so 1/3, 3 times 1/3 is 1. ln of 1, so this has to be 0, right? You check down the graph, ln of 1 is indeed 0. And then
Don't forget the
ln,
-1 though on the outside.
well, I'm gonna do the
Oh, you got that
transform.
later.
Yeah.
Okay.
So then I want ln of 3, which is 1.1 rounded. And then we'll do ln of 6, 1.8. Say it's 1.8. This is going to be a goofy looking graph. I'm going to do a lot of vertical stretch on this. So then my transformation will give me, what's my x? My x is 3x, and my y is y minus 1.
Be 1/3 x because it's a compression.
It is 1/3 x. Yeah. You are right. I'm going to write that as x divide 3. So then we get, what is that? 1/3 of that is 1/9. 1/3, 2/3, -1, -0.1, -0.8. Oof. Okay, that's going to be gross to try to graph. Before I graph this, because the numbers are a little wonky, I'm going to see what the inverse is doing so I can decide, make a better decision about what I want my scale to be. So we have to find our inverse first, right? So we'll have y is equal to ln 3x minus 1. Swap our variables. Add 1 to both sides. Exponentiate both quantities to the base, which is e. Right? Remember when we have base, log, base, argument a, this is equal to just a. So this gives us ex plus 1 is equal to 3y. Erase this part real quick. Okay, that one's not going to erase. That's fine. Oh, hey,
Can
look
you
at that
actually put
erase.
that back? Because I look at your notebook, and that's actually helpful.
Okay, yeah, let me put it back real quick. So this part here, I'll write it off to the side. I'll do this. Log base, I'm writing it too far over. Okay. So if you do base raised to log base b of a, this is equal to just a. And that's what we're relying on in order to go from e to the log base e, because that's all the natural log is, just log base e. E log base e of 3y gives us back just 3y. All right, so then we're going to divide everything by 3. So we get e to the x plus 1 divided by 3 is equal to y, and this is our f inverse of x. All right, so our range is just going to flip around, right? Our domain and range, we can just flip them over from the top. So we'll get -infinity to infinity. We'll get range of f inverse is 3 to infinity, right? And then we want to do our XY table. So we'll flip around these initial points. 0.8. This will give us 1/3, 1 and 2. Our transformations will give us yeah, this is going to be x plus 1 and then 3 times y. So this will give us 1, 2.1, 2.8, 1, 3, and 6. All right, so now I just have to figure out how to graph this. I think what I'm going to do, my y scaling is going to be jank no matter what, but I'll scale it by 2 and see where we get to. So this will be 1, 2, 3, And then we'll say -1, -2, and then -3. So we're scaling everything by 2. All right, so let me go ahead and put it in my asymptotes real quick. Oh, I didn't put in my horizontal asymptote. My horizontal asymptote, where will you be at? Let's see. You will be at y equals 0, right? Which makes sense because it's just the flipped version of the vertical asymptote. It makes sense. Cool. So vertical asymptote is at x equals 0. Oh man. See, like on my notes, I like zoom in a whole bunch of stuff and it's like way easier. Horizontal asymptote. All right. I mean, this is no good. Okay. Cool. That works. And then I want to put in my points. So at 1/3, so like here, about halfway, a little bit less than halfway, we're at 0. So we'll be right here. At 1, we're at 1.1. So like right there. And then at 2, wait, I'm graphing the wrong ones. My life.
Carl is it's Wednesday, my dudes.
It is Wednesday, my dudes. Okay. 1/9, which is 80. I should have scaled this by 3. It wouldn't have fit. It wouldn't have mattered. It's not going to fit. But can I get away with 3? No, because the y's won't fit in the other side. All right, so this graph is just going to be bad. Let's see. So 1/9 is 80 bitty. It's like right here.
Oh yeah, for your y values on the blue one, I think the 0.1 and 0.8 should be positive, right? Because you did y minus
yeah.
1, right?
Yeah. There we go. Okay.
Don't worry, guys. Graphing these is going to be a lot easier because it's just going to ask you what the transformations are.
Okay. 1/9. 1/3. We'll put it right there, whatever. And then 2/3. So not even to 1 yet. We're still below 1. Oh my gosh. All right. So nope, that ain't gonna work. Why would you pick this one?
I told you to use the parent function coordinates. But all good.
Okay, there we go. That was garbage. I apologize for that. Let's try it with the other one. At least we can go to 1 and 1. All right, there we go. That's a good one. 2.1 and 3. So 1, 2. Wait, 1, 2, 3. So around here. And then we want 2.8 and 6. So this is going to be 4, 5, up here somewhere. We'll say this is 6. This one's much easier. Just assume that stays above that. We'll pretend. And look at that, isn't it nifty? This is basically 1 over x, because I say so. If we go to Desmos real quick, so you can see a better graph of this. Okay, so we were at, what were our original functions? ln 3x minus 1, and then e to the x plus 1 plus x plus 1 divide 3, and then we'll just graph x. And look at that. It's perfect. This is just pretend this is the one I did. But yeah, and that's pretty much it. Any questions on any of that?
They're like, what?
I'm assuming that's a no. But yeah, there's a whole bunch of files out there on like these properties.
Well, I
these
think
logarithm
we'll learn
properties.
those ones next time. those properties.
Oh, have we
Yeah,
not done this yet?
No,
Oh,
no, we haven't learned those. Yeah, we haven't learned those
haven't.
ones yet.
Okay, preview. There you go. You're welcome. Remember that. Check the notes to get help on your homework. That's how you trick. That's how you can trick them into doing their notes properly. Is you have to give them hints like that they don't know yet, so they have to come back and reread the notes. I just figured it out.
Are they though?
Man, I don't know. Maybe. I hope they are.
Okay.
I haven't looked at anybody's grades in this class. Come to speak of. Let's see what your guys' grades look like. Let's see whether or not.
Say that for another day.
Yeah, hold on. I got to check my grade too.
He's like, wait, I don't know what my grade looks
Yeah,
like.
say that for another day. All right, let's keep going. We're almost there. So this next one, we'll be solving logarithmic equations. Remember that you cannot plug a negative number into a log, or you can, I guess I should state that better. You can plug a negative in depending on what the equation is, but you cannot take the log of a negative number because whatever number you input has to be greater than 0. Okay, so when we solve log equations, whatever answers we get, we want to check them in the domain. So let's go ahead and start with number 1. Here we have log base 3 of 4x minus 7 equal to 2. So before we even solve this, let's go ahead and find this function's domain. And remember, you take the inside and set it greater than 0. So here we're going to solve for x. X is greater than 7, and x has to be greater than 7/4. So what this means is that whatever values we get for x, they're going to have to be greater than 7/4 in order for the equation to be true. Okay, now let's go ahead and solve this logarithmic equation. And if you're ever stuck in logarithmic form, just remember that you can always convert to exponential. So this means that we're going to take this base of 3 and raise it to the second power. So we're going to get 3 to the second, and then you set it equal to the inside of the log, 4x minus 7. Now, all we have to do is solve for x. You'll get 9 equal to 4x minus 7. Add the 7 over. 16 equals 4x. Divide by 4, and we get that x is equal to 4. Now, does this 4, or is 4, greater than 7/4?
Yes.
Yes. So good. This solution checks out. If it didn't fit in the domain, then it would be considered extraneous. Okay. All good on that one? Yeah. All right. Perfect. 2. Log base x of 64 equal to 2. So again, we want to solve for x. This time, x is in the base. So what we know that from the very first page is that the base has to be greater than 0. So there's no real domain for this log other than that the base has to be greater than 0. Which means all we're going to do here is convert again from log to exponential. So you'll take the base of x, raise it to the second, x squared, and then set it equal to 64. Square root both sides, and you'll get x equals plus or minus 8. Which one do we keep?
The plus.
The plus. So our only answer here is positive 8. Okay, cool. So that is solving logarithmic equations. So you will convert them to exponential and then solve for x. Okay. Next are the fun ones. Here, we are going to solve exponential equations. And to do this, we will convert them into logs as we did on the first page. Okay. So here we have e to the 2x equals 5. So in order to solve this equation for x, we're going to convert it to a log. But since this base is e, we are going to use the natural log. So when we convert this, we are going to say natural log base e of the outside number of 5. So you get natural log base e of 5, and then you set it equal to the exponent of 2x. Now, we know that the base of the natural log is e, so we're just going to rewrite it as the natural log of 5 equal to 2x. And then just divide by 2. You get the natural log of 5 over 2 equal to x. And there you go. Now, if my math lab wants a decimal number, well, I guess we'll see how to type those in. Let me see. Desmos. Oh. Okay. So typing these in, I'm just going to type it in just like I see it. I'm going to use the natural log of 5 divide 2. And we'll do this to 3 decimal places. We're going to get 0.805 is approximately x. And again, we do this just in case my math lab wants decimals. Okay. Doesn't seem too bad yet. 2, we're going to do the same exact thing. So go ahead and convert from exponential to log. Once again, this has the base of e. So we're going to use the natural log. We're going to say natural log base e of 8 and set it equal to the exponent of 2x plus 5. Now go ahead and rewrite this as the natural log of 8 and solve for x. We are going to move the 5 over, so you'll get natural log of 8 minus 5 equal to 2x, and then divide by 2. Is equal to x. Again, a great answer, but if we want a decimal number, then I'm going to have the natural log of 8 minus 5 over 2. And we get negative 1.460 is approximately x. Okay. Any question on those two so far? All right. Okay, that's good. Okay. I think last one. All right. Number 3. 8 times 10 to the 2 minus x equals 5. So once again, we're stuck in exponential form and we want to convert to log, but I cannot convert to logarithm until I get rid of that 8. So what we're going to do is divide by 8, which will give us 10 to the 2 minus x equals 5/8. Now we have the exponential function isolated, so we can convert from exponential to log. This has a base of 10, which means we will use the common log. So when converting, we're going to take base of 10 and make it log base 10 of the outside number of 5/8 equal to the exponent of 2 minus x. And since this log base is 10, we now know it's the common log. So we can just write it as log of 5/8 equals 2 minus x. Now solve for x, subtract the 2, you get log of 5/8 minus 2 equals negative x. Then divide or multiply everything by -1, and you'll get 2 minus log of 5/8 equal to x. Again, that is a fine answer, but if you need decimal, type it in just like you see it. And we get 2.204 is approximately equal to x. All right. And guys, those are logarithms. Only to get crazier from here, I think, whatever I set up for my notes. So we are done.